Hello students, welcome to Inside Physics. Today we are going to discuss about torque and angular momentum. These are the two topics which are related to rotatory motion or circular motion. So, what is torque and what is angular momentum? So, first we will see the definition of torque. Torque is a force which can make a body rotate. So, if you compare this force with a normal linear force, we always defined the linear force which is related to straight line motion. We have defined this force like as it is the physical quantity which can generate an acceleration in a body or object by changing its velocity. So, the linear force as defined in straight line motion or one dimensional motion is nothing but it will generate an acceleration. Acceleration means change in velocity. So when you apply a force on the object, it will impact, the immediate impact is a velocity change. So it will move, the object is at rest, it will gain some velocity by applying force. So the change in velocity obviously gives acceleration. So here acceleration is produced by force. Okay, that's why we have defined the linear force as F is equal to product of mass and acceleration. So this is the concept of force in one dimensional motion. Now we are about to discuss the analogous force, which is torque. It is quite analogous to the force in straight line motion. So this force in rotatory motion is called torque. So it actually makes the body rotate. So when a body, suppose we call in the circular motion, we study about rigid bodies. What is a rigid body? It is a body where all the particles of the body are at fixed distances at, at even we apply some external pressure or force. So the internal distance between the particles will not be changing. Okay, then it is called a rigid body. The internal distance of the particles, the distance between the particles will not easily change, so then it is called a rigid body. So if a rigid body is in motion, generally we mean to say it is in translatory and rotatory motion. So it both having translatory and rotatory. So for translatory motion, force is the cause, and for rotatory motion, torque is the cause. Okay, so here if the rigid body or an object, whatever it may be, if it is fixed to a point, so an object is fixed to a point or fixed to an axis, will be having only one kind of motion, that is rotational motion. It cannot have any translatory motion because it is fixed to an axis. So it is only having rotational motion, and here if you consider it as a door, then if it is having fixed with the hinges, the door is having hinges, the hinges are fixed to an axis, we generally move the doors and open and close the doors. So we apply some force on the door, it will be rotated on its axis, but it will not move because it is fixed. So rotational motion is the one way of having an object fixed at one end or at a point or on an axis. So here we consider the torque and how it is defined. So torque is an analogous force to linear force which can make the body rotate. What is its physical formula? So torque is always represented by a letter tau. It is a Greek letter, we can call it as tau. So this is equal to, we can write it as cross product of the force vector and the distance vector. We will see what is this force and what is this distance vector. So the tau, the torque is defined as like this, cross product of force vector and the perpendicular distance. We will see with the diagram what kind of a example we can have to understand torque. So we know that for a coordinate system we can have the axis like this, and here if we can take a position P of a point P here, and the position vector from O to P can be taken like this, and this is, suppose you can say it is R bar, and another force, a force acting at a point P, we can write the force vector like this acting at a point P. Okay, suppose we assume this is the force vector, this is the position vector, and this is the angle between, we extend these vectors, this is the angle between the two vectors. So the torque, the force which is making this point or object, making it as, you can take the origin and the point, and the distance from the origin you can take it as the distance of this point. So when we make the cross product, what is the way we can write it in the form? The magnitude of torque can be written as Rf sin theta. Okay, Rf sin theta. So if you say sin theta, that means, see, you can write like this, a perpendicular drawn from the line of action of force to the distance. So this is a perpendicular drawn from the line of action onto the position vector. This angle can be taken as 90 degrees. So this is theta. What is this? Can be R sin theta. Okay. So how I got it? Sin theta is equal to opposite side by hypotenuse. That means if you can say this is opposite side, this is hypotenuse, we can say it is x. So x has come as R sin theta. So this is what I have written here. This is considered as x, opposite side. So in this way we can represent a force and a position vector and the cross product of these two. In the beginning what I have written, the cross product of the position vector and the force vector, if you can take the magnitude, it is written like this. So this can be taken in two ways. You can write either as f sin theta, or you can make it as r sin theta into f also. You can write it either way. When you take f sin theta means the f sin theta force component, the force component is perpendicular to the, this is the, if you consider this as force, we can make it as, see, this is theta and this is, which is perpendicular. Okay, can make it like this. This is theta, this is f sin theta, this is f cos theta. So this f sin theta component is perpendicular to the position vector when you consider in this form. If you consider this form, this r sin theta into force, so this is perpendicular to the force vector. So in this way we can define the torque, and torque is a vector. We are always saying force is a vector, this is a position vector, so cross product of two vectors is always a vector. So we can say torque is also a vector. So in what is the direction of the torque? That means the direction of the torque will be perpendicular to the plane of this position vector and force vector. When you can say position vector and force vector are in this plane, suppose xy plane, the torque will be in the yz plane. That is the result come from the cross product. Cross product result, when you take it as r bar cross f bar in anti-clockwise, r bar cross f bar in anti-clockwise, the torque will be, it will be towards you, that means towards the camera. Okay, when you take the cross product as f bar cross r bar in clockwise direction, see the torque will be into the board, that means away from the camera. So in this way you can understand the torque is a cross product of these two. Cross product of a vector, two vectors, is always a vector, and that vector will always be perpendicular to the plane containing the two vectors. So this, see, if you observe this one, r, and what is this, f perpendicular, can symbolize like this. What is perpendicular? Perpendicular of force component to the position vector. You can also symbolize this one, r perpendicular f. That means this is perpendicular to the force vector. This component r sin theta is perpendicular to the force vector. So this torque, what we are doing is for a single particle. You have taken a particular point here, right? Then we will apply this same concept to system of particles at the end of this session. This is about torque. This is quite analogous to the example what we have taken, and the best example is a door which we can rotate on its axis, and another example is a screw. We can see an example of a screw and understand the torque effect in a better way. I will give you a brief example. So if it is a nut or a screw, okay, I will write. So if it is a nut or screw, then we can make this rotate with an instrument called a wrench. We generally do to tighten or loosen some nuts or screws in this way. So this is the center of the screw, and we are making this rotate the screw. This is fixed and this is clipped to this wrench. This will be rotated either in clockwise or anti-clockwise. If it is rotated anti-clockwise, it will be loosened, right? If it is rotated clockwise, it will be tightened. So while it is loosening, it will come out of the board. You imagine like this. If you can tighten, then it will be go into the board. Just like that, we always do have an experience of screwing up a nut or bolt like that, right? If you apply this force like this, force F bar here, what I have written in the torque as R bar cross F bar. So the F bar force vector is applying here, and what is this? I have written as this is the perpendicular distance from the fixed point onto the line of action of the force. This is the line of action of the force. This is the perpendicular distance. This is the angle. We can assume it as 90 degrees. Okay. So this is the force acting on this point, and this will be rotated in the clockwise direction, though the screw will be loosened up. If you apply this force in this direction, you can remove it, and that means we are rotating this in the clockwise direction, so it will be tightened up. So the torque, if you imagine here how the torque will act while rotating this nut in anti-clockwise direction, the nut will move towards us. It will be loosened up and it will come out of the board. That means the torque, because of the torque acting on the nut, it will be coming out of the nut. It will be coming towards us. when you are tightening the nut, it will come go into the board. That is the way torque will apply. Torque is always acts perpendicular to the plane of the force vector and position vector. Okay, this is how we need to understand the torque. Some doubt may occur to you that how this torque is acting perpendicular to the plane of these two vectors. This is the best example to understand the torque. Okay, so this will be applied to a system of particles later in this session. We will understand now what is angular momentum. What is angular momentum? So angular momentum is an analogous quantity to the linear momentum. What is analogous means? Something similar to linear momentum. What is momentum in one-dimensional motion? We have seen in the previous classes, that is mass into velocity, product of mass and velocity. Okay, here if you consider this as linear momentum, which can be calculated when an object is moving with some velocity of mass m, then what is the analogous quantity in rotatory motion? Is there any momentum for an object moving in rotatory motion? If you ask that question, then it is yes. We will be having an angular momentum concept here. The angular momentum is always represented by capital L. So this is also defined as moment of linear momentum. Angular momentum is also defined as moment of linear momentum. Okay, so a torque, in the similar way, we can also express it as moment of force. Okay, this torque, what just we have understood the concept, right? This torque can also be called as moment of force. Whenever we say movement in physics, okay, that means we are actually taking the force and we are taking it in a distributed way. So we are multiplying with some perpendicular distance, and the distance, that means the position vector, I've written as r bar cross f bar, right? So this position vector is actually moving with the force also. So movement of force means how the force is acting on a particle and how it is generating the torque. So while generating the torque, the position vector will also change. Here in the angular momentum, which is also called moment of linear momentum, is mathematically represented as r bar cross p bar, where p is the linear momentum, L is angular momentum. Okay, so what is p here? P is equal to mv. This is angular momentum is for a single particle. Okay, so this is as simple as understanding the torque. Again, the angular momentum will be perpendicular to the plane containing both this position vector and the linear momentum vector. So while understanding the angular momentum, if it is asked what is the direction of the angular momentum of an object rotating in a circular motion, means always take an object in circular motion. If it is rotating in a circle of radius r, the linear velocity will always be along the tangent on the circumference taken at a given point. So the momentum will also be along the velocity. So momentum vector, so mass into velocity, velocity is a vector, so multiplied by a scalar gives a vector. So momentum is also a vector, multiplied by taking the cross product of the position vector. Here the origin is center of the circle and the position vector represented from O to P. If you consider this point as P, this is the position vector, and this momentum of this particle moving with velocity will be this one. P is equal to mv bar. So here the cross product, if you take it in anti-clockwise, it will be towards you and towards us. That means towards the camera. If you take the cross product in the clockwise, it will be away from the camera. So in this case, you can understand what is angular momentum. So there is a relation between angular momentum and torque. We will see how they are both related. If we can differentiate this one dl, okay, dl bar by dt and dt of r bar cross p bar. Okay, so we apply uv formula for differentiation. It can be written as dr bar by dt, okay, cross p bar plus r bar into differentiation of the momentum vector. So in this way, this will be taken and this will become a zero, because the position vector, the distance taken with differentiation to time will be velocity. Rate of change of displacement is nothing but velocity, and this is written as momentum is mv bar. So v bar and v bar are both the same vector, so it will be a parallel, and there will be this will be 0, because the theta between these two is 0. Sin 0 will become 0. If you consider the magnitude, we can write it as similar to what we have done in torque, rp sin theta. Here v bar and v bar are parallel, so theta becomes 0, this will be 0. So r bar into momentum by dt we can write. So this can be written as, this is 0 plus, so r bar, so m is a constant, we cannot differentiate, so dv bar by dt. Okay, you can put a cross here also. So this will be coming out as r bar cross m into what is the rate of change of velocity, acceleration. So this is again coming as r bar cross f bar, r bar cross f bar. Okay, so I will write here again what we have taken, the differentiation, the rate of change of angular momentum. This one we have taken in this way, and we have used uv formula. So we finally got what we got. Here I am writing dl bar by dt is equal to r bar cross f bar. This is what we got by differentiating angular momentum. So here we can easily say with the previous discussion, this is nothing but torque, dl bar by dt, rate of change of angular momentum is nothing but torque. Okay, this is the relation between angular momentum and torque. So if we apply this angular momentum to a system of particles, what we can write? So L, system of particle means if you consider a rigid body or a system of multiple particles, we can write it as total angular momentum of the system having n number of particles will be L1 plus L2 plus L3 up to so on Ln, if there are n number of particles. Okay, so in this way all the individual angular moment of the particles will be added up. So is that same way for the torque also? If we apply So this can be written as this L, total angular momentum, is equal to sigma I is equal to n 1 to n, this is Li. Okay, angular momentum of individual particle, total sum of all the individual angular momentums is equal to total angular momentum of the system. So is it same with the torque also? Torque is always written as, okay, so if we take it as, if the torque angular momentum is taken for an ith particle, we can write it as r I cross. So we can take a single particle, that means r I cross fi. Okay, this can be written as tau I, the torque of an individual particle. If you apply this to number of particles, what happens? See, this will be sigma I is equal to 1 to n dli by dt is equal to sigma I is equal to 1 to n r I bar cross f I bar. Okay, so this will become as tau I. I already written here also. It will become tau I, and this can be in the prefix, we can add I is equal to 1 to n tau I. Okay, this, and here the total angular momentum can be written in this way. What is total torque here for a system of particles? It is tau. So here I am writing the total torque of a system of particles is like this. Okay, so this is the total angular momentum of the system of particles, and this is the torque. Here there is one more consideration. What is the total torque includes? It includes the torque includes torque external plus torque internal. Okay, because it is a system of particle, it is not a single particle. So torque internal plus torque external. So here the torque internal means the torque acted upon between two particles. So if there are two particles, suppose like this, they will be having an action reaction pair according to Newton's third law, and the force between these two particles will be along the line joining. They will form an action reaction pair, and they are quite equal and opposite. The torque contribution because of these two particles to the total angular momentum will be zero, because the forces between them are equal and opposite, they will cancel each other. The torque contribution to the total torque will be zero, because these are having between two particles. If this is applied to total system of particles, all the system of particles will contribute a zero torque, and the net resultant torque will be zero, because they are mutually getting cancelled each other. So here we can put as torque external plus torque internal is zero. Torque internal is zero. So total torque is always like torque external. Okay, total torque of a system of particles we can consider as torque external, means the external force by which it is getting rotated. If you apply some force on it, which is fixed to an axis or fixed to a point, the object will rotate because of the only external torque, and the total internal torque is getting cancelled mutually. That is why it has become zero. So I hope you understood the concept here of torque and angular momentum and the relation between these two. In the next session, we will move to some more topics in circular motion. Okay.